Hi everybody, welcome to the shop. I'm Gerald with Gerald Education. Today we're going to be going over using Newton's second law to solve problems. Now in the last video, everything was static, it wasn't moving, so all the accelerations were zero. That's not going to be true today. All right, we're going to solve three different problems using Newton's second law, how this applies in problems, where the objects are going to be accelerating. And we're also going to throw a little bit of friction into the mix. Okay, so before we get started, if you like my content and it's helping you, please like and subscribe to the channel so I know that I'm doing the right thing. All right, here we go. Okay, so here is the first of the three problems that I want to get to today. So we have a 9-kilogram mass, all right, experiencing a horizontal force of 72 newtons, as shown in the figure. Now, the first thing I want to do is draw a free body diagram. I cannot overstate how important this is. You want to put most of your effort into that, okay, because everything you do is going to come off of that free body diagram. So on the AP test, they usually represent the object as a dot, so that's what I'll do right now. So what we know we have is we've got a horizontal force of 72 newtons, right? We also know in the downward direction, okay, we have a force of mg. Now, depending upon what g is set, either by your teacher or by the AP test or however that works, I'm gonna do these problems with g being equal to 10, 10 meters per second squared. Sometimes you're going to be told to do that with 9.8. All the calculations are exactly the same. The only difference is it's 9.8 instead of 10. I like to do it with 10 when I'm doing a video because it just makes the calculations a little bit easier and a little bit friendlier to talk about. All right. So now what I know I have is I also have force normal pointing up. So let's call that force normal. Okay, so that would be a complete free body diagram for this particular situation. Also keep in mind that mg, since I'm letting g be 10, would be 90 newtons, right? Okay, and this would be 72 newtons. All right, so what I know I have is this. Let's do this separately. Now, I think most of you are going to say, well, yeah, I know it's obvious that Fn is equal to 90 newtons in this case because they're opposing each other, and I know the thing's not accelerating in the up or down direction, and that's fine. You could definitely do that. When I talk about it, when I teach it though, I kind of want you to get used to saying the summation of all the forces, in this case in the y direction, because we're going to look at this in the up and down direction, and we're going to look at it in the back and forth direction separately, and that's a great habit to get into. Okay, so the summation of all the forces in the y direction is equal to the mass times the acceleration in the y direction. Now I know the acceleration is going to be 0, so that's just going to be 0. So what I would end up having when I fill this in is Fn, that's up, minus mg. In this case, that's 90 since I'm letting g be equal to 10, and that would be equal to 0. So then I know Fn is 90, okay? Now you might be saying, well, duh, yeah, I know Fn should be 90. But again, trust me, this is going to come back in a big way later on, okay? So then now let's take care of the x direction. All the summation of all the forces in the x direction is equal to m times a in the x direction. In the x direction, there's only one force, so it's 72 newtons to the right, and that's going to be equal to, now in this case, and again, look at the free body diagram. If you notice in the vertical direction, the forces are balanced. There's a force up, there's an equal force down, it's sitting on a table, we know it's not moving anywhere, so that's why the acceleration is 0. But in the horizontal direction, there's an imbalance of force. There's a force to the right, and there's nothing to counter it on the left. So I know it's going to accelerate. So that's going to be equal to 9 times a sub x. And if I divide both sides by 9, I end up getting the acceleration in the x direction is equal to 8. And the unit on that would be meters per second squared. Okay, so that problem, done. Now we're going to move to this problem where I have friction. Everything else is exactly the same as the last problem, but I do have a frictional force. All right, so the horizontal force is still 72. But now the coefficient of kinetic friction is 0.3. Now the first thing I want to say is this. Well, I'm going to show you what I mean in a minute, but I want you to think of the coefficient of kinetic friction or coefficient of static friction when we get to that. Think of that as a percentage. So think of this 0.3 as 30%. Think of it that way. Okay. Now let's draw the complete free body diagram. So we're going to indicate the mass with a dot. We know we have 72 to the right. we know we have, again, I'm letting G be 10, so we know we have mg down, which is the same thing as 90 newtons, and we know we have force normal up. Okay, so Fn. And now we have a backwards pointed frictional force, which I'll call little f. Okay, now the way this works is friction is related to force normal, and it's related in a really nice, easy kind of way. Now the formula for it is the friction is equal to, in this case, mu sub k times Fn. All right, now that's great, but I'd prefer that you just thought about it as like, oh, the frictional force is just, in this case, 30% of force normal. In other words, when, basically the frictional force is related to force normal in a way where it's a percentage of it. Okay, so what I would have then is this. Let's break this down using Newton's law. And again, I know this is overkill because you can obviously say that Fn is equal to 90. I understand that because those are balanced forces, but I want you to get in the habit of writing it. So the summation of all the forces in the y direction, so right now we're looking here, is equal to 0, right? So I would have Fn is up minus 90 is down equals 0. So Fn is equal to 90, but there's no surprise there, okay? Now, in the horizontal direction, I have this frictional force, and I got to figure out what that is. But what I can say is, oh, I get it. The frictional force is equal to 30% of force normal, which is 90, right? So now I know that the frictional force, 30% of 90 would be 27. So what I have now is, let's switch over, do it right here in this little space. The summation of all the forces in the x direction is equal to the mass times the acceleration in the x direction. So now we're looking in this direction now, right? So in the x direction, I've got 72, that's pulling to the right, minus 27, that's because it's opposing that force, it's opposing the motion, it's not helping it, is equal to mass, which is 9, times a sub x, which is what I don't know and I'm looking for. So 72 minus 27 would be 45, and that's equal to 9 a sub x, which means a sub x would be equal to 5 when I divide both sides by 9, and the unit would be meters per second squared. Done. So there, we answered all those parts. Now, moving along to this. This is exactly the same problem as it was before, but the difference now is the force is at an angle, the horizontal pulling force. So let's do it. Let's do the same thing that we've been doing. Ready? Free body diagram. We're indicating the mass with a dot. Now in this case, we have 72 still, right? 72 newtons. But now it's at an angle. Now it's relevant. I'm going to actually draw the axis. This angle here is 30 degrees. Okay, we know that we have the downward force that we always had of 90, okay? But here's where we have to be careful. In a minute, I'm going to break this 72 Newton vector up into its components, right? But yeah, think about it. This is sort of like, it's like grabbing onto a suitcase and pulling up on it. You're taking some of the weight off the ground. So in this case, force normal, I'm going to draw it in, but I'm going to make it noticeably smaller. You'll see exactly why I'm doing this in a minute, okay? And we also have a frictional force pointing back, okay? All right, this is getting ugly, but it's not as bad as you think. Watch. If I break this up, the 72 Newton vector, I have to break that up. I'm going to break it into a horizontal component here, okay? And this is going to be 72 times the cosine of 30. If you're unsure about that, go back and watch my videos on breaking up vectors. And then there's a vertical component here, which is going to be 72 times sine of 30, okay? And just as a quick note, we're really just looking at this right triangle there when we break those vectors up. 72 cosine of 30 is equal to 62.35. And 72 sine of 30 is exactly equal to 36. And here's my frictional force. Okay. Let's do what we've been doing, okay, because nothing really has changed. So the summation of all the forces in the y direction is equal to the mass times the acceleration in the y direction. But again, we know this is a mass sitting on a floor. So in the y direction, in the up and down direction, it's not accelerating, so that's going to be 0. So now if I list all my upward forces, so look at the picture again. These upward forces have to balance with this one downward force in the y direction. So I know I have this. I've got Fn, which I don't yet know, plus 36, because the 36 is helping pull it up. And then minus 90, because that's going in the other direction, is going to be equal to the mass, which is 9 times 0. So this is just 0. So I have Fn minus 54 equals 0. So that means Fn would be equal to 54 newtons. Okay, so I found Fn. Now that's significant because since this 72 Newton force is sort of pulling up, it's taking some of the weight off, which is lowering Fn, which is what we saw, all right? But now I'm taking 30% of this new Fn, this lighter Fn. It's not 90. So what is 30% of 54? Okay, so the frictional force is just going to be 30% of 54, which turns out to be 16.2. So now I know the frictional force right here is 16.2 opposing the motion. So now I'm going to do the summation of all the forces in the x direction, and that's going to be the mass times the acceleration in the x direction. Now in the x direction, I have a force of 62.35. That's this one. And then I've got friction opposing it. That's this one. So it's going to be minus 16.2. And that's going to be equal to 9 times AX. And I'm looking for AX. So 62.35 minus 16.2 is equal to 46.15. And that's equal to 9A sub x, which means A sub x is going to be equal to 46.15 divided by 9 when I divide both sides by 9, and I get 5.13 roughly. And the unit on that would be meters per second squared. Okay? Done.